Okay, so welcome back to the continuation of this topic on the non-concentration. And in the previous lecture, we talked about how the non-concentration is connected to the subsets of the like these subsets of the random walk. So we had this this theorem that we mentioned in the notes that I think this was a lemma. We mentioned that if A is a subset of ZP and A is not contained in a coset of proper subgroup of ZP, then there exists n in n such that this A to the plus n is equal to ZP. Yeah. And then as a consequence of this, we wrote this theorem 3.30 that let mu from ZP to 0, 1 be a probability distribution then the like analogous statement in this context, the support SPT mu is not contained in a coset of a proper subgroup of ZP if and only if there exists n in n such that the support of the convolution is equal to ZP. So how can you read this theorem in the language of the random walks? Is basically that when you start to operate the random walks, when you like think about the support. So if you think about this this support here, this is basically kind of the trajectories where the random walk exists in the context. So when we have this, let's say the let me keep this up here, and maybe I draw a circle here, and we start to walk with the random walk. So if we started from these 2 points, let's say in Z4, and we start to walk the random walk, then we start to equidistribute. So let's say we have this this kind of a distribution, then it starts to, even if we started from 3 points here, when we start to apply the convolution, it starts to spread the mass into every direction. So we start to actually contain all the points that we had in the group. So in this like example, when you have only 4 elements, it's quite trivial. But when you have like let's say several elements, like in a much like bigger subgroup, let's say you have a few points over here, then eventually when you start walking these the subgroup using these weights, you will end up to basically covering the whole big group with this convolution. So it kind of spreads around the space in many ways in this example. And what we can do here is have this proof of this. So we can use the previous lemma to just prove this statement. So let's have a proof. And we apply it with just this support. So let SPT mu, the support, if you remember, this is just the set points in ZP where the mu t has positive mass. And, and let's prove the statement with this direction over here. And the previous like theorem basically tells us the following. So first of all, of all, we have, of course, that the support of the convolution is equal to, this was the theorem we had before on the, that connected, I think in the notes I used the notation, I think this was theorem 3.14 in the notations, but if the numbering changes, it's basically the that connects to the support and the convolution. So this becomes basically with the notation A plus n. That's the convolution notation. And thus, by the lemma above, we have, because we have now the assumption that if it's not contained in the proper subgroup, A satisfies the assumptions, we have the following, that there exists an n in n such that A plus n is equal to ZP. And now this was equal to, well, we can just put here directly the SPT mu star n is equal to ZP, because this is equal to A plus n. So this direction is basically the lemma we already proved, but then to the other direction, if you want to do the equivalence to the other direction, so suppose on the contrary that the SPT mu is contained in some proper subgroup gamma, where this is a proper subgroup. Okay, here I'm taking this assumption that it is the whole, it's actually contained in a subgroup. So if you want to take that it's not contained in a coset of a proper subgroup, that's another argument that we need to add. But I'll have first a case when it's just not contained in a proper subgroup, because then you can quite easily see what happens in the situation. Because now here this implies that the support of the mu star n, which is now remembered by the sum position, but this is actually, because this is a subgroup, this is actually equal to gamma, because as gamma is a subgroup. Okay, and so basically we have that also SPT mu star n is contained in a proper subgroup, okay, of ZP, because we assume that this is a proper subgroup gamma, so it's also contained in a proper subgroup. And because it's a proper, this implies that SPT mu star n in particular cannot be equal to ZP, because it's a proper subgroup, so it basically is contained already in a smaller set, so it has to be not equal to the whole space, which in particular implies that there exists a T in ZP such that this mu star n T is equal to 0. So it has to have a point where it doesn't have any mass in it, and this is a contradiction with the statement that we were saying the whole support is the whole space ZP. So contradiction with the SPT mu star n being equal to ZP, which would prove the claim if we have the problem. So now there is still the case that if it is actually contained in a coset of a subgroup. So now you can actually think about yourself. So what if it's instead of contained in a proper subgroup, you have actually a coset of a proper subgroup, as we have in the statement. So what happens then is then you can go into you can look into the proof of this, the previous statement as well, that if A is not contained in a proper subgroup, then it has its properties. So if it's a coset, then how would you basically would need to translate at every stage the statement, that you would translate it here by minus t, and then you would have to think about what happens to the large sums of these cosets. So I leave that out here. You can try to look into that statement. How would you modify this proof with cosets? But in the case, what would the details be different in that situation? Okay, so this is quite important now, because now we basically have a way of characterizing using the support of the probability distribution whether it actually spreads into the whole space by just using the cosets of proper subgroups of this ZP. And actually this is like funny, because in the ZP case the subgroup situation is very trivial, like the kind of, as I said, that basically you can generate them by a single elements typically, and there's like this kind of very basic structure in them. So that's why in that situation it's not that difficult to see what actually happens. But in general, this theorem is actually quite important. If you go to more general subgroups of more general groups, it's actually very important, because it allows you to really concentrate on the small subgroups to get the statements. And okay, in the next lecture, I plan to go into the final topic in this series, and that's about the ergodic theorem, which then is connecting to the subgroups and the kind of chaos properties of the random walk into this using this theorem that we just stated. Okay, so that's all. Thanks.